All right, next up we have Paul Barford. Paul, here he comes. Paul was unfortunately a victim of the ice storm in Atlanta last time, and we convinced him to stick with us and make it to Bellevue. So thank you very much, Paul.
Good to see you. Is there a mic? Oh, just right there. Okay. All right. Well, after support from the organizing committee, I'm very happy to be back here to speak to this group today about a project that we've had going on in Wisconsin for the past couple of years. This is exactly the group that I've been eager to talk to for quite some time because sort of squirreled away in our academic setting and talking to other academics, we have a certain perspective on connectivity that may or may not be congruent with the perspective that this group has, so I'm very eager for feedback on our work. So the general aspect that we're interested in is understanding physical topology of the internet. And of course, when the internet was first invented, way back when, and for a period of time after that, there were lots of napkin drawings and other representations that were probably pretty accurate in terms of the node locations and physical conduits that facilitated connectivity. However, sometime in the 80s, and probably people in this room have a better perspective of it than I do, things grew to a level of complexity where it became impossible to have any one entity have a comprehensive understanding of what the infrastructure from a global perspective actually look like. And while we draw fun diagrams like the one on the right here, the famous peacock diagram, of course we know that those don't have any real basis. In fact, they're very pretty, but they don't necessarily relate to the actual nodes and links that comprise the internet today. So the objectives of the work that we've undertaken are to create a catalog, a comprehensive database of what I'll call the physical internet. The physical internet being defined as the geographic locations of infrastructure, nodes that house routing and switching equipment, and the physical links that connect those nodes together. So this is not the layer 3 based maps that a lot of people, especially in academia, have spent a lot of time trying to understand, but nodes of the actual physical infrastructure. Beyond the physical infrastructure, then our objective is to take a constructive approach of adding metadata to that repository, metadata including IP addresses, the ability to augment that metadata with actual capability to emit active probes from those locations, to include information like BGP updates, and then also to include pieces of information that may not necessarily immediately be obvious, but based on the ability to ascribe a geographic location to that data, things like weather reports or earthquake reports or other things, we'd like to build this comprehensive repository. Beyond simply gathering the data, the objective of the project is to actually produce a portal that allows the data to be visualized and analyzed, and then ultimately, since we're a research entity, to finally take the step of applying the maps that we've put together to research problems of interest, right? So if you've ever read a paper about internet topology, it always starts out with some kind of preamble like the need to understand physical structure can be applied to understanding application performance, robustness, blah, blah, blah. Well, we'd actually like to start to use the maps to address those problems. So probably many people in the room are related or are familiar with related work in this area. Maybe some of you remember the Sean Gorman story. Anybody remember that story from about 10 years ago? Yeah, one or two people. If you haven't read that story, it's kind of amazing. This was a an effort that's very much like ours that resulted in kind of a breathless set of articles that were published in the Washington Post about how could anybody possibly think that putting together a repository of the connection infrastructure of the internet could be anything other than a horrible security problem waiting to happen. And long story short, Mr. Gorman was allowed to publish his thesis that was based on this, but aspects of the thesis were actually classified, and he had to finish his work in a SCIF facility, and it was a little crazy at the time. There have been related efforts, especially organized around gathering measurements using layer 3 techniques at CADA, in Israel, the DIMES project, and right across the street here at UW in the iPlane project. And of course, there are the commercial activities, the relevant commercial activities from the groups that are listed. The other project that's most related to ours is the Internet Topology Zoo effort that's been carried out at University of Adelaide in Australia. So what does it take to compile a physical repository of the internet? Well, first and foremost, we rely on search to find maps of the physical locations of infrastructure. And while I'm guessing that most of the people in the room here who are responsible for operation, maintenance, and development of physical infrastructure are not big proponents of publishing maps of that infrastructure, the folks in your sales group love to have maps of physical infrastructure. So we use a variety of, we've become very facile in developing search terms to identify maps of networks. We've gathered thousands of these maps over the last couple of years. And then what happens after that is the very, very tedious process of transcribing those maps into a GIS database. So while we've tried very hard to automate that process to the extent possible, because of the wide variety of representations, both in terms of how the maps are actually presented, whether they're a Flash application or a PNG or some other kind of representation, there's a lot of variation in what we've found, and at the end of the day, we have to default to manual transcription. The good news is that undergraduates are very inexpensive and are very happy to have $10 an hour kinds of jobs for these things. So we employ them as needed to do this transcription project. Unfortunately, undergraduates are sort of universally sleepy people. And when it comes to actual transcription, you can actually stand behind them and watch them make errors when they do these transcriptions. So the process of verifying the data that's actually entered into the database is likewise tedious and something that we pay a lot of attention to. At the end of the day, if we're entering data that's wrong meaning an incorrect reflection of the maps that we've actually found, then obviously the data is useless. So this sounds like a sort of a horrible effort in terms of scope, but the fact of the matter is that the number of physical locations in terms of POPs and conduits that are deployed across the globe is much smaller than the number of IP addresses and so forth that are deployed across the globe. So while this is a big undertaking, maybe at some level it's tractable, and certainly the development of new infrastructure takes place at a much slower pace than deployment, let's say, of new systems and new configurations of systems. So I'm just going to go through a couple of maps here that you're probably all very familiar with, but the fact is that when you start digging into maps that you can find in search, the number and variety of representations just kind of boggles the mind. And so you find maps like this one of Telstra. Actually, my favorite map, and the one that I always use in talks for smaller bodies, is the great representation of level 3. Are there people in the room here from level 3? Probably somebody, maybe not willing to raise your hand. Anyway, your network map is beautiful, and the thing that I love the most about it is that when you drill down on level 3's maps to the finest grain, what you can see is that their links have actually been geocoded. And this is not something that we see in many maps. So if I go, for example, to Sprint's map, here is a case where the links are not geocoded, and the locations of the infrastructure are simply given as cities, okay, which is not nearly as useful as a lat long or an actual street address. So in everything that we've had to do when it comes to creating this repository, we've had to develop different techniques to regularize the data that we put into the database. Ultimately, we love street addresses. And street addresses, of course, are available from certain infrastructures, like level 3's, for example, but not from others. So in cases where we can't find a street address, we will simply place a POP in the centroid of a city, or if there are locations of infrastructure that have street addresses, we will sometimes simply bind what would otherwise be a location fixed to the centroid of a city to an existing POP. And of course, all of this is labeled in the database. Of course, for infrastructure where we have information about services, oftentimes that's accompanied with these maps. So, IP services or voice services or other types of services will include that metadata in our database as well. One of the things, so here's an example of a regional fiber layout in the state of Illinois. One of the things that we have recognized is that while labels are often not included in maps, if you consider infrastructure along with other representations, for example, rail and highway, you can oftentimes geocode links with that existing infrastructure. So for example, there is a path here that goes from Chicago down the sort of the right central portion of the state of Illinois. I happen to grow up in that area, so I know very well that that is actually following Interstate 57. And in cases where we can match network infrastructure with existing physical infrastructure, we will add those labels as appropriate. Okay, so we have drawn the line at city level fiber layouts. I'm sure that many of you are aware that these kinds of city level fiber layouts are actually available for certain large cities in particular. Of course, again, the motivation for this is that the sales folks want businesses in those areas to see that they have the ability to connect to your infrastructure in a very straightforward fashion. This is downtown Chicago. We have not endeavored to add these kinds of details to our database. If you think that adding nodes and links on a sort of a national or regional level is tedious, doing street level fiber is incredibly tedious in the mapping infrastructure that we've developed. So we have these maps, we just haven't included them in the database. So our effort began in September of 2011. We have endeavored to be broadly focused in terms of the data that we've gathered. We've developed different methods for regathering maps from URLs that we've entered into the database, and to the extent possible to automate the verification of maps that are in the database versus recently crawled maps. We have built a comprehensive web portal based on ISRI's ArcGIS, which is the canonical GIS tool used broadly in many different disciplines. And the benefit of ArcGIS is that in addition to giving us some nice flexibility in terms of visualization and analysis, it enables us to very easily include different data sets that have been developed in different areas. So we had a paper in the SIGCOMM Hot Planet workshop last fall that describes Atlas If you want to take a look at it, I encourage you to do so. I'm going to give you the URL for the portal at the end of the talk, and I'm eager to get your feedback on it. Let me just say quickly, too, that the way that we've set the system up, we are trying to pay attention to security. Right now, I'm the key. So you can get a very, very cursory view of the portal without credentials. If you want to actually look at the full view of the system, you need to send a request to me to get those credentials. We don't give out the raw data right now. But eager to have people, especially from this group, take a look and to help us understand how we can make the portal more useful for you, or if it's useful in any way for you right now. So the current archive as it stands is that we have nearly 400 networks included. We have included over 2,000 data center locations, NTP servers, DNS servers, IXPs. We have getting close to 15,000 nodes from different networks. In terms of unique locations of nodes, nearly 8,000. The total number of links in the archive is nearing 14,000. And recently, we've begun to expand the scope of the networking-related data to include Wi-Fi hotspots, cell towers, and so forth. So here's a snapshot of the full view of the current archive that you can get from the portal, including both nodes and links. We actually, if you're familiar with GIS, GIS is a visualization capability based on the notion of layering. So we actually have quite a few different layers in the database right now, including all of the different networking data and weather reports. We have road and rail infrastructure, and can easily add different layers of different types of data, again, because of the fact that we've built this all on ArcGIS. Okay, so I'm going to shift gears to the second half of my talk now, and spend a few minutes telling you about a study that we had published at the end of the last year, end of 2013, in the ACM CONEX conference. And this is one of the first applications of the Atlas database to a problem that I'm going to assume that many in this room have had, and I'm eager to understand what techniques various groups in the room use to address it, which is understanding how to equip your infrastructures to deal with issues of outages that are potentially caused by natural disasters. So in this study, we're seeking answers to a couple of questions, which is how can we automatically adjust routes to avoid outages before they happen, so generally to improve robustness. Another way of saying this is if you had to add one link to your infrastructure to improve robustness from natural disaster outages, where would you add it? So that's a question that we seek to address. And then also to consider a real-time application of this capability, namely, as a threat is evolving, so think about, for example, a hurricane, how can routes be established that lower the risk of outages in the face of that kind of a threat? So to answer this question, we developed the notion of bit risk miles, a metric that we call bit risk miles. And the idea behind bit risk miles is to consider several different components in the form of a single metric that enables us to make these kinds of assessments versus standard shortest path routing. So generally the notion of a bit risk mile is to include the bits sent, or a proxy for bits sent, which I'll talk about in a minute, plus the distance between 2 points, plus the risk of outage of either the endpoints or the link between endpoints, and that's what we mean by bit risk miles. So you consider a path being composed of multiple hops between two nodes. Then the notion that we develop, captured in the formula at the bottom of this slide, is that we consider the distance along with the risk and the number of bits sent on the path. Okay, so the idea here really is that what this gives us is the ability to quantify the trade-offs between a shortest path between two nodes that might have a higher aspect of risk versus a longer path between those two nodes that has a lower risk of outage. Okay, so I'm going to define a couple of terms in the prior equation, and the terms are as follows. One is that we have, as I say, this number of bits sent, which is essentially the cost of an outage if an outage takes place. Well, we don't know the number of bits that are being sent over any particular link at any time. This is something that, of course, you would have information about. So what we do to approximate this value is we use the fraction of population that might be affected by an outage, meaning the fraction of population that's actually clustered around a particular pop. Secondly, we consider actually two aspects of risk in this study. One is the historical probability of outage, so this is a static notion, and we consider this using a corpus of events that we gathered from FEMA and NOAA over a period of 40 years. So this is, of course, available to anyone. But one of the nice things about these data archives is that they give detailed information about the particular geographic locations in which the events took place. And then we also include a dynamic component, which is the forecasted probability of risk as it relates to physical locations in the path of, again, think of a tornado or a hurricane. And this would be information that would be available from the National Weather Service or National Hurricane Center in terms of an evolving threat. So what we've developed in RiskRoute is essentially an optimization framework that allows one to identify and assess the trade-offs between distance and bit risk miles. I make statements here about current techniques based solely on what I've read in the literature and sort of not based on your operational experience. So we'll be interested in hearing your feedback again about how you manage these issues. Of course, storing all backup paths is probably not something that is feasible. So what our framework allows is a comparison, or the way that we apply it in the paper is by a comparison between simply shortest paths between two nodes and the expanded path that's identified to lower risk through our optimization framework. So to consider this for the purpose of the paper, we looked at the network infrastructure for 7 large ISPs and 16 regional ISPs in the United States. This is something that gives us, or our framework gives us, the ability to consider intra as well as inter-domain routing. I'm going to wave my hands a little bit at inter-domain routing because I do not know the details of every single one of the routing peers that exist in these networks. So we made certain assumptions about that based on the data that we had available. Obviously, our framework can be applied in your setting using your detailed knowledge of that. And what we're interested in terms of the study is assessing 2 different features. One is the ability to reduce the amount of risk by adding additional paths using the RiskRoute framework versus the distance that winds up the expansion in distance between the 2 points that is a result of adding these additional paths. So this is a slide that I'm not going to spend a huge amount of time on, but basically from the intradomain perspective, there are a couple of sort of take-home messages that I want you to have, because obviously the networks, the 23 networks that we considered for this study all have sort of different characteristics in terms of their proximity to historically risky areas, and in terms of the richness of their connectivity, in terms of the full geographic their footprint, and so forth. And the sort of the take-home here is not going to be maybe particularly earth-shattering if you think about it, but basically the graphs on the left side of this slide tell the following story. For networks that have a larger geographical footprint, they tend to be more robust to internet outages than those that have a small geographical footprint. And generally, networks that have a larger number of POPs, namely richer connectivity within their infrastructures, are more robust to outages and wind up having less path expansion in the dynamic case than those that have a fewer number of POPs. On the contrary, and the graph in the upper right is somewhat mislabeled there. It shouldn't say average router degree, it should say average POP degree. Just because you increase the amount of connections at a particular POP doesn't necessarily mean that you've reduced the bit risk miles. And likewise, simply by increasing the number of peers for a particular network doesn't necessarily mean that you've helped yourself either. Okay, the last results slide, actually in the paper, there are a lot more results about how to apply RiskRoute. Just emphasize again that it's a general optimization framework to help to identify where and how backup paths can be included in your network. This slide represents a set of results that show for a particular set of networks how adding the most optimal backup path within those infrastructures can help to reduce bit risk. And what it shows is that, in fact, level 3, given its large footprint and rich connectivity, has the smallest impact by adding the most optimal link between two nodes in their infrastructure. Okay, so they're doing pretty well. But on the other hand, a couple of the other networks, Sprint and so forth, could potentially increase their robustness by adding additional links in their infrastructure following the RiskRoute technique. Okay, so this is a little animation just for fun of Katrina and level 3 and how level 3 could have adjusted its routes based on the RiskRoute framework. So what you see here, of course, is the footprint of level 3's infrastructure, the path of Katrina, and then the highlighted path is the one between two selected nodes in the infrastructure, the nodes that had the highest bit risk as the hurricane advanced, and how paths might have been augmented in order to reduce bit risk during that event. So this is a demonstration of the dynamic capability of RiskRoute. All right, so next steps, we're working hard to continue to populate the database. As I say, we currently have around 400 networks in the database right now. All the big ones are easy. The hardest networks are the local and regional networks. We have, as I say, a large archive of maps. And I've got, hopefully, a small army of undergraduates this summer who are going to be working on making those additions. really the hardest task that we face from the long-term perspective of making this a worldwide compendium is that neither my Russian nor my Chinese is particularly good. And in order to identify maps in other parts of the world, there may well be language components there that we'll have to consider in our search. We're spending a lot of time working on the web portal and in terms of expanding and making its capability more robust. We're very interested in developing new techniques for adding metadata to the portal. And one of the recent things that we've added that we hope is potentially useful for this group is the ability to actually run active probe-based measurements, ping, trace route, and a tool that we also developed called Path Audit along using connections to 850 different endpoints across the globe. Planet Lab makes up a large percent of that, but Looking Glass servers do as well. And one of the things that just becomes very clear is that our lack of ability to do good IP geolocation really limits some of the visualization capability that we have in the portal now, so we're going to be spending more time on IP geolocation as we move forward. Okay, that concludes my talk. Only 25 seconds over, so pretty good timing. Here is the URL for the portal. Please take a look. If there are those of you who are interested in accounts, send me email, pb@cs.wisc.edu, and hopefully we've got time for a question or two. Thank you. People are hungry.
Hi, Ralph. Is it on? Ralph Mullen, Internet Archive. Are you interested in crowdsourcing input regarding infrastructure and outages?
Yeah, we've talked about that. So on the database slide that I showed, we are actually beginning to include information from wiggle.net, which is a crowdsourced portal. So yeah, the answer, I think the straight answer is yes.
All right.
Thank you.
Thank you, Paul. All right, we'll be breaking for lunch now. We have a welcome lunch next door here, co-sponsored by Comcast and Juniper. And at the Regency Ballroom, we have the newcomers lunch, sponsored by VeriSign, where we'll have a little more content in there, help direct newcomers how to get the most out of the conference. Thank you very much. See you back at 1 o'clock.